Okay. Hi, everybody. In the coming lectures, I will illustrate several examples where we use LabVIEW control design and simulation toolkit together with LabVIEW-based Kalman filter. I will begin with simple educational demonstrations and then progress to more complex and interesting applications. At the outset, it's important to note that LabVIEW Control Design Toolkit relies heavily on arrays and matrices. Since working with Kalman filter also requires configuring multiple matrices, it was naturally integrated with state space analysis from the beginning. LabVIEW has achieved this integration very successfully, and the Kalman filter is embedded within the control design state space framework. As a simple definition to Kalman filter, we can say that this is an algorithm which provides an optimal estimate of system variables. By thus, it shows how a system is going to change given noisy measurements and imperfect knowledge about the system. Important to note that in addition to maintaining an estimate of the state, Kalman filter tracks an estimate of uncertainty associated with that state. In other words, at every time step, there is an estimation of the variables in the state vector, and there is also an estimation of the uncertainty of the prediction. This uncertainty can be represented by a matrix known as the state covariance matrix. If we consider the figure below, here it is, it shows how Kalman filter fits within the control design toolkit. This is the system of interest, the control system block. It could have one input or many inputs. Suppose we are working with one input u of t. This is the forcing function to the system, and this input must be supplied to Kalman filter simultaneously. Now, the output of the system, which is supposed to be noisy, is fed to Kalman filter also as an input. Here we assume that the output, if the output of the system is clean enough and there is no noise, so we can add a noise to simulate an output, a noisy output of the system, and it is fed to Kalman filter. So Kalman filter, which is designed by LabVIEW, has two inputs. The first input is that input which is fed to the control system itself, and the other input is the output of the control system, which needs to be treated to get an idea about the more accurate instantaneous values, estimates, in other words, of the variables in this control system. The outputs of Kalman filter here, I have shown here two outputs. One is the estimate of the output value, and the other one is the state estimate. If we go to LabVIEW, if we go to LabVIEW and open LabVIEW, I shall show you how it looks like. Now we are opening LabVIEW. This is the version 2021. Yes, now we go and open a new virtual instrument. This is the front panel. This is the block diagram. In the block diagram, now, I shall right-click and go to the Control and Simulation Toolkit, and then to the Control Design. In the Control Design, I can go directly to Implementation, and from there to the icon Control Design Discrete Kalman Filter. This is the Kalman filter icon in LabVIEW. We have more other icons. I shall talk about it in time. Now, if we want to see what is there inside the output of the Kalman filter, here we click the help, show context help, and now if I put the cursor here, we shall see that at the output here, this is the estimated output which I have shown. It is called estimated output Y hat of K. Hat, it means estimated value. Of K, K is the variable, which means that this is a discrete output. For every step, time step, we have a corrected state estimate also. It could be used, and also we can use the predicted state estimate. We shall see that Kalman filter first makes predictions, and then it corrects these predictions to give this value. And also we can get at the output the Kalman filter gain. There are two types of gains in Kalman filter. Kalman filter gain M of K and Kalman filter gain L of K. And as I said also, at the output, it gives an idea about the uncertainty of prediction by showing filter error covariance, as you see, and predicted error covariance. So a lot of variables, detailed information, really we can get as the output of Kalman filter. But at the input, as you see, we have only two inputs. The input U of K here means discrete input. If it is continuous Kalman filter, this should be T, time. And if it is discrete, yes, it is how stochastic and discrete at the same time here. And in addition to the input U of K, we have the output of the control system. This is the output not of Kalman filter, it is the output of the control system which feeds Kalman filter. And here, important to note that this noisy input is important, and Kalman filter at least needs one variable, noisy variable, feedback to the filter so that it works. Now we know a little bit about Kalman filter itself. Let us continue our talk also, which we have begun with just now. So I open the page again. So we are here. This is the input. This is the other input. And this is the representative outputs as we have seen just now. Important to say from the same beginning that there should be a match, a high degree of matching between the system, the controlled system, and the dynamics of the algorithm of Kalman filter. If the system is nonlinear, then Kalman filter alone doesn't work, and it doesn't give accurate results, and we need to work with another version of Kalman filter dedicated for nonlinear system. It exists also in LabVIEW, and we can work with it. It is called extended Kalman filter. Okay, now also at the beginning, I want to say that Kalman filter itself is a mathematical algorithm, and this is really a complex algorithm, and the derivation of Kalman filter is also very complex, very complex. So we do not gain too much if we will spend a lot of time in order to make derivation for it. This exists in literature anyway, and it is not necessary for practical use. Okay. Another important thing here in Python, for example, one must explicitly implement the prediction state or step and the correction or updating step and the propagation of both from one state to another. Doing this involves a lot of concepts such as the initial state estimates, and process noise covariance and measurement noise covariance. What do we mean by the innovation? And also evolving of the innovation from step to one another step. What is Kalman gate? Why it is used and how to use it? And all these concepts are to be implemented in a predefined sequence and to be repeated in a recursive manner. So for me, I found it is advantageous to work with LabVIEW than to work with Python with these explicit numerous steps. In LabVIEW, all what you need is to feed, to define the input U of t or U of k, and the y of k, which comes from the output of the control system. And the algorithm will be implemented without participation of any other body. Yes. So, as a summary, I wanted to say that working with LabVIEW-based Kalman filter, you not need to manually implement the prediction or updating equations, and you simply need to configure the matrices that define the dynamic model of Kalman filter. In advance, I can tell you that Kalman filter can work with two dynamic models, one of them with constant velocity, we shall work with it, and the other one with constant acceleration. This is a major advantage compared with textual programming languages as Python. So, as you see, really it is not necessary to derivate Kalman filter algorithm and to prove it. It's more necessary and more important to save time to work with examples, and we shall go this way, and I shall refer to you about some equations which are included in the algorithm without derivation. Okay, now let us go and learn more about Kalman filter. So, Kalman filter, as I said, is integrated within the environment of control design and simulation toolkit. This means that you should know about this toolkit because you cannot work without sufficient knowledge about this toolkit and how to manipulate it. This toolkit represents control systems by using the transfer function models or by using the zero pole gain model or by using the state space model. Of course, for us here, especially for Kalman filter, it is more interesting to work with state space model. As state space model, as I said, works by using matrices, and the same thing applies to Kalman filter. In order to work with Kalman filter, the state space model must be stochastic. So you need to input a stochastic space model. Also, in order to add the required covariance matrices, we include or feed a second order statistics noise model. Here it is. I can show you again so that I am not talking in theory. Here, let me tell you, let me go again and open and work with a Kalman filter. This is the Kalman filter. When we shall work with Kalman filter, it must be configured. And configuration of Kalman filter could be done internally and could be done externally. If we want to do that externally, now I double click the icon. This is the page and this page which I am going to work for to configure the Kalman filter. Here you see we have stochastic state space model, and these are the details of the model. How many inputs you want, 1 or 2 or more, how many states you want to work with, number of outputs, what is the number of the noise elements in the process noise vector, and the sampling time, and these are phi and G and G and C and DH. These are the matrices of interest. Now, if I want to configure the Kalman filter externally, I should click this arrow and click terminal and OK. Now here I shall have a terminal called stochastic state space model. If I right click it and create a control, for example, so this is the input which represents the stochastic state space model. In order to add covariance matrices, again, I double click it and go to the second order statistics noise model. And again, I tick on the terminal. OK. Now I have also another terminal here. This is the terminal. OK. Create control. This is the second order statistic noise model. The contacts are given on the front panel here. Sorry. Double click it. Here they are. So this is one which includes a matrix G and B, matrix A and C and D and H. We shall know about it in more detail. And the other one is another cluster, which includes the covariance matrix H and the measurement matrix R and the correlation matrix between Q and R. So now I do not want to save anything here. Don't save. I have shown you only these things to understand what is written here. You also can create stochastic state space model, as I have created just now, and the second order statistics noise model, so that you can configure the matrices necessary to work with the state space models. State space models may be single input, single output, and maybe multiple input, multiple output. And really, when working with a control design, we can convert the transfer function to a state space model and vice versa. We can convert the deterministic transfer function to a stochastic state space model. We can make a lot of conversions, which is required to make the design easier. We shall also cover this through examples. Yes. So now, as a beginning, I want to explain to you the deterministic state space model equations. This is the discrete. The continuous I did not include it. I don't need it now. We are working with a discrete time steps. Step here is k plus 1. It begins from k and continue to x to k plus 1 and then k plus 2 and so on. X here represents a matrix, which is the state matrix at step x plus 1. Here it is x of k. It is the matrix, state space matrix at step time or time step k. So this is the value after one time step. This is the value of x of k after one time step. It is equal to the x of k multiplied by matrix A plus matrix B multiplied by u of k. U of k here is a vector of inputs. B is a matrix which is called input matrix. X of k, this is a vector of states. The states could be the variables, one or two or more variables. A is the state matrix. It is called state matrix. This is the first equation. This is the state equation. The second equation, which is the measurement equation, y of k is equal to matrix C multiplied by x of k plus matrix D multiplied by u of k. So here we know u of k what it is, and we know X of K. What it is, see here is a matrix. It is called the measurement matrix. This discrete description of the state space model without noise, without any disturbance. But we are interested in stochastic state space models because, as you know, the output of the control system is always noisy, and the control system at any part of it is always exposed to the surrounding media, and it is always possible to pass a noise to the system, and so the system is stochastic in nature. So we need to generalize this set of equations to a stochastic form, stochastic state space model. The stochastic state space model, as you see here, of course, includes the basic equations here with an addition which explains or defines the noise and disturbances which affect the control system. So X now of K plus 1, the state of the variables at the step K plus 1 is equal to A multiplied by X of K as it is here, plus B U of K as it is here. But we added here another term, which is G multiplied by W of K. W of K here is a vector with a number of noises, stochastic noises, random noises, which affect the system. G is a matrix. It is just a mapping matrix which relates the noise vector to the states. The noise vector to the state. The other equation is Y of K is equal to C multiplied by X of K again, plus du of K again. But now we added another two terms. The other term is again W of K multiplied by H. And the third one is V nu multiplied V nu of K. This term here, as you see, means the physical meaning that the noise vector here, which affects the state, may also at the same time affect the measurement, the output of the control system. So this matrix here shows the degree, the percentage of W of K which affects the measurement. Nu of K here is representing the noise associated with the sensors and other noise sources which affect the measurement, nu of K. So as you see, the stochastic model now becomes more complex, and there you need to work with these terms which represent a random noise. Usually, in Kalman filter, we consider this noise as a Gaussian noise, a normal distributed noise with a mean equal to 0. This facilitates to make the computations easier and more understandable. As you have seen before, in addition to the stochastic state space model, we need to include a second-order statistics noise model, which represents the covariances of course, of the process noise and the measurement noise. Here really is an expression which shows the detailed mathematical expression. This is the expectation of W multiplied by W transformed minus the expectation of W multiplied by the expectation of T, transposed expectation of W. But I have said that we deal with W of K and nu of K as Gaussian noises with a zero mean value. This makes this part, this term, to become zero. So again, Q is expressed as the expectation of W multiplied by W transformed, which is really the covariance matrix. This is the covariance matrix, which represents the uncertainty related to the Kalman filter model, or yes, model, or dynamics model. R here is also another covariance matrix, but it is related to the measurements. Nu here is also another matrix which takes in consideration the correlation between Q and R. But generally, there is no correlation between Q and R, or we ignore it because it is very limited, and so nu will become equal to zero. As you see, this is not easy to comprehend and to understand from the first time, but you see you have here a lot of information about each element which is included within these equations. And let us go through it and talk about it. K, I told you this is a number, the number of the time step in a discrete stochastic model, and it begins from zero and ends with 1 or 2 or 3 any number. X is the state vector, which means that this represents the number, not the number, the elements of variables. What are the variables there? Velocity, level, viscosity, temperature, whatever it is. All these variables are gathered together through the vector x of k. Important to note that one of the advantages of using state space analysis is because it is easier to work with multiple variables, multi-input, multi-output control systems. U is the input vector. Also, it is a vector which represents what are the inputs there. Y is the model output vector. This is Y. W, as I told you, it is a process noise. It is vector also. The number of noise elements is Q, and because it is a vector, it is multiplied by one column only, and a Q value or Q rows, number of rows, Q. New here is R multiplied by 1. R is the measurement noise vector. Also, we can have more than one source of noise in the measurement side. A depends, this is the matrix A. Here it is. And its dimension depends on the values of the variables within x of t, of k. If the number of variables is n, so IA must have n multiplied by n dimension, which means n rows and n columns. B, which is the input matrix, has n rows and m columns. C is the measurement, or sometimes it's called observation matrix. It also relates the measurements to the number of the state R multiplied by N. D R multiplied by M. Now, N is the number of states. It's okay. I have told you, explained to you that. Number of model inputs is given a symbol M, and R is the symbol which we use to show the number of outputs, and Q is also the number of the length of the process vector. G and H are arrays, are matrices, which are used when working with when including the second order statistics noise model. And one of them, as you see, the mapping G, or weighting or mapping, has a dimension nu multiplied by Q. H related to measurement, and the number of measurements and the output R multiplied by Q. Q, this is the covariance matrix. It has the dimension Q by Q, R also R by R. If the number of states is 2, so then Q will be 2 by 2. Well, as I told you, really at the same beginning, maybe it becomes, or it shows somehow difficult, but when you read it once or twice, you will be familiar with all these detailed information. Here, a small talk about the process noise GW of K, which I added, or which is added here, GW of K. This part or this term, which is added, how it affects X. Generally, it is a noise. And this noise itself makes some deviations to take place in the values of the variables. This is the essence of what I wanted to say. So what is it? It is a random disturbances that affect system dynamics. Is it created by us? No, it is not created. It is naturally existing and depends on the inaccuracies in the system dynamics or in the model of the system. If the model is not accurately given, and there are some things which are not taken in consideration, some variables, so we can say that imperfection of the dynamics model, this imperfection is shown as a process noise here. So shortly speaking, G W of K is a random push into the state equation. Why? It is in the state equation. Look here, the state equation. Here it is added as a push, which increases or decreases, a random push into the state equation with a strength described by Q. The term H multiplied by W of K is the same nature, except that this process noise appears in the measurement. This is less common, not always existing, but it means the same process noise W of K also leaks into the measurement. It affects the measurements. Here is an example for them. Suppose you are working in a positioning system and you use the GPS receiver, which measures the position. This might be influenced by atmospheric noise that also perturbs the dynamics. This atmospheric noise affects the state, and at the same time, it affects the measurement. Anyhow, the role of H is really limited, and it is a percentage about 1%. Usually, it is taken as about 1%, 10%, 5% of the whole process noise, which affects the system. So, shortly speaking, H multiplied by W of K is a projection of process noise into sensor output or the measurement part. The last thing here is V of K, which represents the noise from the measurement side, which is as a result of the imperfections related to sensors used to generate a feedback in the control system. Here is a summary about all these additions. So GW of K, it appears in the state equation. It's a random disturbances entering the dynamics. They affect the dynamic model used in the Kalman filter. HW of K appears in the output equation because it is part of the GW of K. It is also some disturbances leaking to measurements. V of K, it appears only in the output because it is related to the sensors, independent of sensor noise, added directly to the measurement equation here. Here it is. Okay, with this, I finished today's lecture. I know that it is somehow abstract and somehow mathematical and not easy to comprehend, but it is really the simplest way I am trying to show you, because Kalman filter indeed is a very complicated algorithm. In the next lecture, I shall try to show you how the different equations of Kalman filter look like and how they are implemented and the sequence of their implementation. And then we shall move on forward to define the matrices required, and then we will begin illustrating typical examples. Okay. Thank you for listening, and see you in the coming lecture.